Okay, we have covered sections in chapter 1, and now we continue the section 1.5, quantifiers. Quantifiers. Here, P of x is a statement involving the variable x. When D is a set, then for each x in D, the P of x is a proposition, means when P of x is a proposition, we call P of x is a proportional function or predicate with respect to D. And this is called the domain of discourse, okay, of P of x. Okay. P of x is a property that element of x has, which means set of x in capital X such that P of x means this is a set of all element x in X such that P of x is true. Okay. So propositional function and domain of discourse and the meaning of a set with a proportional functions. First example says the statement P of x, which is n is an odd integer, then P of n is a proportional function with the domain of discourse is positive integers. Okay. Then this P of n is a proposition because we can decide whether the P of n is true or not. In this case, this proposition is false because when the domain of discourse is G plus positive integers, this statement is not true for some integer, positive integer n, such as n is equal to 2. For example, P of 2 means 2 is an odd integer, which is not true. So this proposition is proved to be not true. Okay. If P is a propositional function with the domain of discourse G plus, which is a positive integers, then it's this propositional function for each of n, which is P1, P2, P3, da, da, da. Each of these Pi's should be either true or false. Okay. Propositional function. So before we've learned the propositions, just one statement. Now, with the domain of discourse, we have many statements. We call it a function, propositional function with the domain of discourse. Okay? In this propositional function, and each of this function for each value of n should be either true or false. Okay? So it's a kind of generalization of propositions. The propositional function with domain of discourse is P, then statement this. For every x, P of x, if and only if, we can write for all x, P of x. We call this statement is a universally quantified statement of P of x. And this symbol for every, this symbol, flip of A, capital A, the symbol A is called a universal quantifier. Okay, so for all x, P of x is true, means for all x, whenever x is in the domain of discourse, then P of x is equal to true. Okay. This means this. the statement for all x, p of x is false means there this p of x is false for at least one x in D, which means if this is false means there exists x in the domain of discourse such that p of x is false. Okay? And this p of x is called the counterexample of this statement. 무슨 말인지 이해되죠? 언제나 true, 이게 for all x에 대해서 p of x가 false란 말은 그것이 true가 아니게 하는 적어도 하나의 x가 존재한다는 것만 보이면 된다는 소리고 그 하나가 그것이 true가 아니게 하는 counter example이다 이렇게 얘기한다는 소리예요. Okay, so consider the universally quantified statement for all x, x square is bigger than or equal to 0. Okay, then this should be true whenever x is a real number, okay? Because x squared is always bigger than or equal to 0 for all real numbers. So this is a true statement. For the universally quantified statement, when we say this, when we say for this universally quantified statement is false, that means there exists at least one x in the domain of discourse such that the proposition is false. Equal counter. The same, yeah, it's the same word. Next, universally quantified statement. This for x, x square minus 1 is bigger than 0. Okay, is it true or false? This is false because if we choose x is equal to 1, then 1 square minus 1 is equal to 0. 0 is not strictly bigger than 0, so it's false. And 1 is a counterexample, okay, to the statement of this. And this is a pseudocode to check this universal quantified statement, whether it is true or false. So from di to the dn, it will check each of the statement whether it is true or false with this code. We can easily make a Python code of this to check the given universal quantified statement is to be checked to be true or false. And yeah, this algorithm is explained here to be checked. Here the x, variable x is called a free variable, and the variable x in the universally quantified statement here is called a bound variable, or a bound variable. Here. And also for all x p of x, if and only for all x p of x, which means for any x, yeah, p of x is. They are all the same, equivalent, if and only if. The symbol A may be read as for every, or for all, or for any. Yeah, for every, for all, for any. That's the same meanings. Next, to prove for all x p of x is true, and we must every value of x in the domain of discourse and show for all x p of x is true. Okay. Yeah, that's clear. Yeah, for all x. So yeah, for the domain of discourse D, yeah, we write for all x in D, p of x. So this is the when the domain of discourse is given as D, and this should be the proper notations. Next example, discussed the universally quantified statement for x in R. If x is bigger than 1, then x plus 1 is bigger than 1, strictly bigger than 1, is true. Okay, this is true. We have to show. Yeah, in order to verify this statement is true for every real number x, yeah, we can think of two cases. The first case, the x, real number x can be either less than or equal to 1 or x is bigger than 1. There are only two cases if x is a real number. When x is less than or equal to 1, then what about this statement? X is less than 1, and if x is bigger than 1, then such and such. Here, x is less than or equal to 1, and also x is bigger than 1. So there is no such x. So the assumption is false. So whether the conclusion is doesn't, whatever conclusion do we have, still this whole statement is true. So we call it a vacuously true. So if x is less than or equal to 1, then there is such, and this there is no such x that satisfies this. So this statement is always true from the tautology. So all we have to do is consider this case. If x is bigger than 1, then conditional proposition, this is x is bigger than 1 and x is bigger than 1, then x plus 1 should be bigger than 1. You see? Because this left-hand side is bigger than 2. So this is true. So in both cases, this statement is true. So this universally quantified statement for all x in real, if x is bigger than 1, then x plus 1 is bigger than 1 is true. So you had asked questions on tautology before. Okay, here. Yeah, consider the existential quantified statement here. There exists x such that satisfies this one. So we try to solve this. Then we can easily find the solution of this equation, which is 2. So if we substitute x is equal to 2, then 2 over 2 square plus 1, which is 2 over 5. So it satisfies this equation, which means there exists x which is 2 such that it satisfies this. So this existentially quantified statement is there exists x is equal to 2 that satisfies this. So this is a true statement. But this is not true for all x, because there is other value that does not satisfy this. So here, existential quantified statement. Here, to verify that existentially quantified statement of this is false, there exists x in real such that this, but this is not true. Yeah. In order to show this statement is false, what we have to do? We have to show this. We have to show that 1 over x squared plus 1 is bigger than 1 is false for every real number x. If we show this is false for every real number, then it is equivalent to show that there exists x such that this is false, isn't it? So we have to, in order to show this existentially quantified statement is false, then we have to show it is false for every x in real. So we can show it. The 1 over x squared plus 1 is bigger than 1. It's false when this is false when this is true. So we must show this is true for every x in real. Yeah, we can show that 1 is less than equal to x squared plus 1, and 1 over x squared plus 1 is less than 1, and true. This is true for all real numbers. So it's been proved. So since 1 over x squared plus 1 is less than or equal to 1 for every real number x, the other direction should be false for every real number x. Okay, so we can say that this existentially quantified statement is false. Okay. Next, suppose that P is a propositional function whose domain of discourse is the set di's. Then the following pseudo code determine whether there exists x such that P of x is true or false. Okay. We check whether P of di is true or false from 1 to n. And this has been coded here, so you can see in here, chapter 1, section 1.5, first code, and yeah, this is true. Yeah. This is always true. And the code, pseudo code was given there, and the second one is, this one is always bigger than 1. This is true. And the code that we made, and this, this is always true. It's less than or equal to 1. So which means this is false. And this pseudo code was made. I will make it to finish up. Okay, anyway, show. Next, the concept. Loop examines one at a time to check all the things. Okay, anyway, alternative way to write there exists x such that P of x means for some x, P of x, or for at least one x and P of x. So the symbol E may be read there exists or for some or for at least one. But there exists x such that P of x is more popular. And next, and generalized Morgan's law for logic. Okay. When P is a propositional function, each pair of propositions in A and B has the same truth table. Either both are true or both are false. Here, this statement is equivalent to this statement, and this statement is equivalent to this statement. See the difference. Negation of this make this A to E for all to exist, and the plain statement to the negation. All you have to do is, in parentheses, change A to E and plain to the negation. And B, the negation of this statement makes E to A and plain to the negations. So all you have to do is, in parentheses, if you have negation of whole the statement, then change E to A or A to E and plain to negations. That's all you have to do. These are equivalent. You can easily check these are working. Like you see here, the negation of this is proposition. This negation of this is if this is true, then this is false, which means if this is false, which means there exists x in the domain of discourse such that P of x is false. Okay, which means P of x false for at least one x in the domain of discourse, which means the negation of P of x is true for at least one x in the domain of discourse. Okay, so because of this observation, we can find, and this, if this is true, then this is true. So De Morgan's law for logic gives us a very easy way to have an equivalent statement. And next, The proposition is that every rock fan loves the U2, which is the Irish rock band from Dublin. Right? Its negation symbolically and in word. Have you seen this? Do you know the U2 band? This he was a very popular rock band when I was young. Do you know U2? No? Yeah. Anyway, what's the negation of this? Then first write down this in symbolically. Okay? Let's say P of x be the proportional function. X loves U2. X loves U2, the band. And then the every rock fan loves U2 means for all x, P of x. So for all x, x loves U2. This is the statement that we have. Then what's the negation of this? Negation of this is equivalent to A goes to E and plane goes to negation. So there exists x such that not P of x, which means the negation of this proposition is there exists x such that a pen don't like U2. Negation of this. A pen x, there exists a pen x who do not love U2. That's the negation. So when you do find the negation, all you have to do is just to change it. Change it the opposite. Everything. One at a time. Some negation of this in symbolic. Some birds cannot fly. So P of x says x flies. Then this statement can be written as some birds cannot fly. There exists a bird who cannot fly. Okay? So what's the negation of this? Negation of this is E goes to A and negation over the negation gives us plane. So this is, which means every bird can fly. For all x, x can fly. So every bird can fly. That's the negation of this. So instead of writing in word, you can make more clearly by using symbolic notations to find the negation. And universally quantified proposition generalize the proposition of this. Okay. When you have a set of propositions, then for x, P of x can be generalized as proposition this, P of I is true for every i's. For all x, in P of x is true, if and only P of x is true for every x in the domain of discourse. Okay, here. So these PI's are replaced by an arbitrary family P of x like this. Then x for every x in the domain of discourse, that's the P of x. This notation can be simplified like this, like what we did before. So we can use all earlier notations without any difficulties to deal with the set of statements. For example, the domain of discourse of propositional function P is -1, 1, 0. Then propositional function for all x in P of x is equivalent to this and this and this. This and this and this. So all three are satisfied. So this statement can be simplified in this way in notation. Okay, and this disjunction, conjunction and disjunction, and this junction can be simplified as with this existential quantifier. Or, which means there exists such that at least one that satisfies some of this. So there exists x that satisfies this. Means there is x satisfies at least one of these. Isn't it? The same word can be replaced with it. So you can use the same mathematical logical statements what you have learned for this set of propositions, statements. And the domain of discourse of proposition P is 1, 2, 3, 4. Then there exists X, P of X is equivalent to these are true. Which means there exists some that satisfies it. Next, rule of inference for quantified statement. For all X, P of X is equal to true. P of X is true for every X in the domain of discourse. In particular, D is in D, and P of D is true. The argument is valid. The rule of inference is the universal instantiation. 전칭 예치화, 추상적인 것을 구체적인 예를 통하여 표현한다. Okay. The rule of inference is universal instantiation. For all X, P of X, therefore, P of D is true if D is in D. Okay. This statement can be written in this way, and these are this is called universal instantiation. Called universal instantiation, and P of X for every D in D is called the universal generalization, and there exists X such that P of X. That means P of D is true for some D is in D. We call this rule of inference is called existential instantiation. And P of D for some D in D means there exists X such that P of X also existential generalization is called. So this is some of the definitions here. This is my mistake. Given that for all n in this, this is what you mentioned, isn't it? Here we should make this is n. This is not x. So you should write it as n to make it understandable. Okay. For any positive integer n, for any positive integer n, sorry for okay. For all n in positive integer, n square is bigger than n. Using universal instantiation to conclude, 54 is a positive integer and 54 square is bigger than or equal to 54, which means this is true for every integers. So whatever number you put in, that conclusion should be true. That's what this example wanted to say. Not proof. And this kind of proof will be proved by mass induction in the later chapter. Write the following argument symbolically and then using rule of inferences to show that the argument is valid. Here, for all x, if x is an integer, then x should be a rational number. So this is valid. If this is valid, then if this is valid, then q is not rational. So square root 2 is not rational. Therefore, square root 2 is not integer. If this is a valid statement, then because of that, if for square root 2 is not rational, if square root 2 is not rational, then square root of 2 cannot be an integer. That's what it wanted to be said. Okay. Okay. If you use it with those instantiation, then P of x denotes the propositional function x is an integer, and Q of x denotes the propositional function x is rational. Then this argument becomes for all x in R, if P of x implies Q of x. Okay, if it's integer, then rational. But here, square root of 2 is not rational, can be written as Q of square root 2 is not rational, so negations like this. This is true. From this is true statement, and this is a condition. Then from here, for all x, this should be true, but this is not true, which means this cannot be true, which is p of square root 2 is not true. So p square root 2 cannot be an integer. Okay, that's concluding. This is not an integer. Okay, this argument is called universal modus tollens. Next, last section, nested quantifier. Consider the statement, sum of any two positive integers is positive, then addition is positive. The domain of discourse is of two variable proposition function is R close R. Okay, cross product, cross. And multiple quantifiers for all x, for all y are nested quantifiers. Nested quantifiers. Okay. For all m, there exists n such that m is less than n. In word, what it means? The domain of discourse is the set G close to G. Okay, G and G, the integers and integers. And for all m, there exists n such that m is less than n. What this means? What this means in word? These are integers. Which this means, if you choose any integer, any large integer m, still there exists a bigger integer than m. Which means there is no largest integer in the set of integers. That's what it says. This means for every integer m, there exists a bigger integer n such that m is less than n. Which means there is no greatest integer. That's what it says. Okay. This short statement says this in meaning. The proposition everybody loves somebody, L of xy, be the statement x loves y. Then everybody requires universal quantification. Somebody requires existential quantification. Okay, here the symbolic logic of proposition is for all x there exists y such that L of xy, which means for every person x there exists someone y such that x loves y. That's what it says. This says for every person there exists someone who loves y. That's what it says. There exists a person y such that x loves y. That's what this sentence says. Okay, but here there is x for y such that of xy. This means someone loves everyone. There is somebody that somebody loves everybody. This statement, someone loves everyone. So in this case, as you see, the A, E, and EA, the order of quantifier is important. It changes the whole meaning different. And this are totally different meanings. Okay? And the domain of discourse here. For all x, for all y, and this implies this. Okay, domain of discourse is real, close real. The conditional proposition, this is true. Hence, the statement is true. In word, for all x and for all y, if x and y is positive. X is positive and y is positive, then x plus y is positive. The sum is positive. That's true. Always. So, for all x and for all y, this statement is true. Okay. Condition. And also for all x, for all positive x, x is positive and y is positive, then product of x and y is positive. This is true for every real numbers as well. And for all x and for all y, this implies that. Let's see. X is positive and y is positive, but and which implies x plus y is not 0. No. If we choose x is equal to 1 and y is equal to minus 1, then x is positive and y is negative, but addition of that is equal to 0, isn't it? So it violates this. This is false. So x is equal to 1 and y is equal to 1 gives us an example, a counter example of the above statement. And the discourse, domain of discourse is here. The following pseudo-code determine whether this is true or false. We are using two subroutines to check all the cases. Indexing I and j, and check for each I, check all j's, and for the next I, check all j's. That will check all the possibilities. You can use this lab to check. For all x, there exists y such that x plus y is 0. This, for all x, there exists. Yeah, this is true. If someone gives me x of any real number x, then if I choose y as a minus x, then x plus minus x should be 0. So there exists such y all the time. So this is a true statement. So this is a way of writing. For all x, there is y such that x is bigger than y. This is false. For all x, there exists y which is less than, for all x, there exists y which is less than y. Okay, if x is equal to, in positive integers, yeah. If it's all real, then it's true. But if domain of discourse is the cross product of positive integers, then if we choose x is equal to 1, then there is no smaller positive integer y for x is equal to 1, because that's the smallest positive integer. There's no positive. So this statement is false when domain is G plus cross G plus. But this statement is true for real cross real. So domain of discourse is important. When we do have a domain of discourse of this cross product of this many, then we do have more subroutines to check all the cases. That's the difference. And the statement for there exists x for all y such that x is less than or equal to y. Then this statement is true because there exists at least one positive integer for which x is less than or equal to y is true for every positive integer y. Okay. Every positive, whatever positive integer you choose, that integer cannot be less than 1 because of the domain of discourse is G plus. For 1, there exists x is equal to 1. And for all others, still x is equal to 1, work for every y's in G plus. So that's true. But this is false because less than or equal to y. Because if we choose y is equal to x plus 1, then it's always bigger than. Then this y is always bigger than x. So in G plus, that is false. Something like that. Example. Similar. Yeah. There exists x, there is y, such that this is true. This is false because if we choose 7, then xy is equal to 7, then x is positive and y is 7 is a prime number. So prime number is not a product of two integers. Okay. So one time is the x and y cannot be other than one is x is 1 and y is 7, or vice versa. Other than that, there's no positive numbers, integers, x and y that whose product is 7. So because it's prime numbers. And for x, negation of this is like what you said, what we said. Negation of this is a goes to e, and parenthesis and negation. Then negation goes to e goes to a, and the negation of this part p. So it gives us the negation of this statement, easy, by generalized De Morgan's law for logic. Okay, negation goes make this goes to e, and the negation of the last, and negation of this make E goes to A and plane goes to negative. Okay, so all you have to do is just in negation and switch A and E, interchange it. And write the negative of this. Right of this is negation of this is negation of this is E goes to A, and negation of all the rest here. And negation of this makes A goes to E, and negation of this. Negation of this is x, y is bigger than or equal to 1. So negation of this goes. So all you have to do is to do it one at a time. So, and you can make a code to find the negation of given statement with this. Okay, so that's true. I think that's the end of it. This is the last part, last example. You must have seen this, limit of f of x when x goes to a is equal to 1. Here, this can be written as for every delta which is 0, there exists small x such that this implies that, which can be written as for delta there exists epsilon, positive epsilon, such that this implies this. This is exactly equivalent to this limit. This is called this is actually starting point of analysis. This is the kind of microscope of mathematics. Microscope for the function. We can really analyze very detail of the function with these notations, which you have learned in this chapter 1. I think that's it. There are some examples and problems that you can solve for chapter 1. Then we will continue chapter 2. Before that, we do review chapter 1 and start chapter 2. So read. Any questions?